This is a combination of a science story and a political science story. I have Al Snyder as a person who contributed to the paper, and his colleagues, Al's retired colonel, Al Ramsey, or Lee is a retired colonel, Al Ramsey's a retired colonel, Ed Beard is a retired Chief Master Sergeant, Art Bowright is a retired colonel, Peggy Shea and Don Smart, who live in this general area there in New Hampshire. They were civilians who were working during this event or the immediate aftermath. Trey Cade is a colleague of mine, so a little bit more in my generation, a retired lieutenant colonel. Ian Hewins and Bob McFadden work at the National Center for Atmospheric Research, where I have a joint appointment. Bill Denig is also from Air Force Research Laboratory. He is currently he is the director of the Solar Terrestrial Environment Group at the National Center for Environmental Information. And Liam Kilcommons is my research assistant, and he keeps me and the whole train on the track. So what you're looking at here is a diagram, or not a diagram, it's an actual photograph that was taken at the Sacramento Peak Observatory in New Mexico at 1840 UT. So that would have been just before noon Mountain Time. So it was midday in the U.S. And the image was taken by Damastis and Stover, I think. Do you remember Stover's first name? I don't remember their first names.
Howard Damastis.
Howard?
I don't know Stover.
I want to say Roland or Roger, something like that. So anyway, they were civilian observers who were working for the Air Force, also trying to keep an eye on the sun. And the title here is McMath Region 8818. So we have known for a very long time that the sun produces regions of kind of knotted up magnetic field, and that knotted up magnetic field can trap charged particles, which as they gyrate around the magnetic fields emit radiation. And this region right in here is where there is radiation being emitted in the H-alpha portion of the spectrum. So H-alpha is essentially hydrogen alpha. It is actually pretty close to visible light, and what it does is it pretty much outlines where there are regions of very intense magnetic field. These little dark regions here are regions of cooler gas that are suspended in the sun's atmosphere, and they also outline some regions that could erupt and send material out towards Earth or out into space, but generally they are much more gentle in their eruptions. Sometimes you'll have these kinds of structures just rotate across the disk of the sun, go around, come back again. If they do, they get a new region number. There's probably at least 3 regions, maybe 4. This one was just 8818. It had been seen in the previous couple of rotations, and it was seen one more time 27 days later. And 27 days is the rotation rate of the sun. Earth rotates every 24 hours. The sun rotates every 27 days. So it's much more massive and a little bit slower rotator. So with that as a kind of a background picture, we'll go forward, and not quite that forward. And so I want to tell you a story about behind this solar storm and how we came very, very close to a situation where people didn't really know what was going on with this incredible burst from the sun, and really thought that we were being jammed in advance of attack by the USSR. So that would have been one of the ultimate societal consequences, because during mutually assured destruction we would have responded to assure the destruction of the aggressor. And that went both ways. I mean, certainly the Russians, the Soviets thought the same thing. So I'll tell you a little bit about the political circumstances and spend more time on the solar situation and how and why, maybe not why, but how this great burst took place, and then tell you a little bit more about what was so great about this storm. So, as I've mentioned, the sun can be active. It's considered to be a magnetically active star. many stars are magnetically active, meaning one of the way they shed their energy, and almost all stars rotate, so they spin up their magnetic fields and it gets twisted and they need to shed that as well. So stars that are active shed energy and they shed this twisted up magnetic field, and one of the kind of footprints of those magnetic fields, if you actually look at the sun with the appropriate glasses, I never recommend looking directly at the sun, it's a bad idea, but with the appropriate filters, you can sometimes see these footprints of where there's very knotted up magnetic field. If you look at it in a slightly different wavelength than the ultraviolet, you'll get a different sense of the distribution, how the magnetic fields actually arch up into the atmosphere, and where they're trapping this plasma, this charged gas that can radiate, and it radiates across almost all portions of the electromagnetic spectrum, not only the visible, but the ultraviolet, the X-ray, and the radio as well. And there's always plasma in motion, it's always radiating in X-ray, sometimes a little less so, sometimes more so. It's always radiating in the radio portion of the spectrum. And so in the 1960s, what we were able to see was visible, and not only across the full visible spectrum, but in that very special wavelength called H-alpha, which I just showed you, which is H-alpha is essentially one of the emission lines when an electron that should be attached to a hydrogen atom if it were cold gets kind of attached, and then it drops down in its energy band, and it can pop back up and drop down again. So that's how we get the light out, as it's moving up and down in those energy bands. And then we also see right above these regions, high up in the sun's atmosphere, kind of outlines of these magnetic fields in X-ray. So that's a fairly modern view that we didn't have when Lee was on duty in 1967, but we did have some views of the sun, the visible, and we also could hear the sun being really, really active in radio when these regions passed by. So here's a diagram that I use in my class that shows you a little bit more of a perspective. It's just a cartoon from the side in terms of what those loops might look like that actually attach down to where there are sunspots. And there are great loops. They're millions of miles up into the solar atmosphere. And these loops are just constantly being jostled because the sun really boils. It has a 6,000 degree surface, and just like in a pot of oatmeal that you might put on in the morning, there's all kinds of motion going about as the energy tries to get out from the bottom of the pot, and that jostling motion will mix up these field lines. And because field lines are vector quantities, they have both direction and magnitude, sometimes you can get field lines that go this way, and if you force magnetic field lines to come together in places where they're strong and oppositely directed, you can actually make the field line go away and it gets converted into energy, which then comes out as light, or it comes out as energy that's available to really push or accelerate particles out into space. And that is what happened on this particular day. So the things that we need as kind of a background is we need to know that the sun is buoyant, and that buoyancy can twist these magnetic bubbles or field lines into ropes, and that is happening day in and day out, but there's actually a cycle to it. The sun has an 11-year activity cycle and then a double cycle, or another cycle sitting on top of that actually changes the magnetic field so that the fields flip every cycle every 22 years. And I'll give you a picture of that. So this is the sun rotating. Unlike the Earth, where we rotate as a solid body, the sun actually rotates a little faster at the equator than it does at the poles, and as a result, the magnetic field gets a twist. And as you twist up magnetic field, in many cases, It's kind of like a rubber band that you've really, really twisted up, and you'll notice when that happens, it wants to kind of loop out. And so sometimes you get these little outbursts, they're little here, but they're actually these huge bubbles of magnetic field that will attempt to kind of release some of that tension. And in the process of doing that over 22 years, you can actually take the sun's magnetic field, which in this case was coming out of the North Pole and going into the South Pole, and you'll end up flipping it so that the South Pole is now here and the North Pole is here. And that is something that we see not only happening on our own sun, but we can infer happens on other suns or stars as well. So that is the cycle, and every 11 years we tend to get these structures where we see more and more of these sunspots concentrated at latitudes that kind of go from mid to low latitudes. Here's a modern picture of what one of those loops looks like. Down here are the sunspots. This is extreme ultraviolet, and we can see these loops. They kind of come up here to a cusp. So this is our cartoon that goes with it, and we're looking for places where we might be bringing these magnetic field lines together in some kind of opposite directed magnetic field lines so that we can release energy. And what's off of the top here is sort of the top part of this bubble that has been shot out into space, and it's called a mass ejection. And I think the first time I learned about mass ejections, coronal mass ejections, was in Nancy's class. And I was just so fascinated that there were all these structures on the sun that I couldn't see with my own eyes. She had somehow this incredible 3D version that she could show on a chalkboard. And so now here I am trying to continue this, but no chalkboards present. Anyway, so here's the structure again, and we're going to be kind of concentrating on what happens when these kinds of structures get really, really complicated, which they can do. And so here's another modern view of this, and now we can see here in the foreground there's this loop, but in the back there are others, and there are others, and you can see it's kind of a tangled mess. And the more tangled it gets, the more energy is being stored, and the more the sun wants to try and get rid of some of that excess energy. And here's just a little bit later, and you can see all of these beautiful loops with the electric charges just gyrating about them, outlining what those field lines look like.
Where are these pictures taken from?
This one, I believe, they are taken from space. In order to see extreme ultraviolet or X-ray energy, you actually need to be above the atmosphere. We are mercifully protected by our atmosphere, and that atmosphere absorbs the X-rays and the extreme ultraviolet. So to get images like these, you have to be in space. And I believe this is a slightly older image. I'm thinking, I don't really know which satellite. It was TRACE. Transition Region Active Something Explorer. The U.S. goes to great lengths to come up with an acronym for every satellite that goes up, and sometimes it's a little bit tortured. But I do remember it's a transition region. And transition region refers to a layer in the sun where the sun's temperature changes very, very drastically, and as a result you do get a lot of very different kinds of emission that you can actually associate with temperatures in the sun. So we can take the sun's temperature by just using filters on spacecraft and saying, oh, now I can see this structure, and I know in order to excite particles that would be stopped by that filter, the temperature would have to be X or Y or Z. So these are just gorgeous images, and so now I will remind you that these have to be false color, because our eyes only see, the Roy G. Biv, red, orange, yellow, blue, part of the spectrum, green and ultraviolet, I guess. And these are in the extreme ultraviolet, meaning our eyes don't see them. So we get to, scientists get to do great things. We get to bring out our coloring books and decide what color we're going to make these loops so that we can make them visible to talk about and explore. So here we have beautiful orange loops, but it's all false color. It's just like if you were looking at the radar today before you came and you saw that there was some green on the radar, well, you knew that that was rain, right? But rain isn't green. It's how we color it up so we can think about it. And you might have even noticed that someplace up in northern New York it was purple, and so there's a little snow falling up there. We do the same thing with the very common imagery that gets displayed. So let's have a green sun. And so what you're seeing here is just a movie of how dynamic some of those arches are, and what's been overlain here is where it is that the most intense X-rays are coming out, and where the particles are the most heated. So most of the background is extreme ultraviolet, but then the coloring here is what kinds of particles are trapped on those magnetic field lines. And what you don't get to see very well, although I know is happening, is as these arches are moving about, there's probably mass that's getting expelled up here. And it's actually what's going on in these loop region legs, and however they might interact with other loops around them. That is where we believe that the radio emissions from radio bursts can actually come out and put out energy that was frankly unthinkable in Lee's day and remains somewhat unthinkable. So as I mentioned, the sun does cycle, so I just thought I'd show you a new, relatively new image. There's been some scientists working on just how many sunspots are there. So we count sunspots as a scheme, as a method of determining just how active is the sun. And every time you get a peak, well, that means it's pretty active. So here in 1959, about the time that the Russians launched Sputnik, sun was pretty active. So in late 1950s, early 1960s, there were a number of reasons that Department of Defense, the nation in general, Air Force in particular, were interested in monitoring what was going on. We knew that cycles where there were lots of sunspots, there were likely to be a lot of effects on technology. And the other part of it was, suddenly we have operations in space with Sputnik launched, and you know the U.S. was going to go there immediately and had actually been involved in bringing up a space program. But when the sun's energy interacts with the upper atmosphere, it expands, heats up the upper atmosphere, and if you have a more heated upper atmosphere, the satellites that are moving through that experience more drag, and then their motions are altered. And you go, oh, okay, so it experiences a little drag. Well, ultimately that means it's going to come down, and you would like to be able to predict when it's coming down and maybe where. You would also, we now know that it's really good to put, reserve a little bit of fuel so that you can actually direct where it comes in, maybe send it into the ocean rather than, heading it towards Belfast, Maine or anything like that. So, there's a number of reasons that in the late 50s, early 60s, Air Force became much more interested in this whole situation, to the point that they actually started sending some of their young officers off to various science programs at University of Colorado Boulder, for one. That's where Lee went. Amazingly enough, I've ended up there. I went to UCLA as part of this program in the 1980s, and there's just been an immense number of people, hundreds probably, who have gone through programs that help them prepare to understand what impacts might be on DoD systems and on technology. And not only do we count sunspot numbers, but we actually count where those sunspots are. And I just thought I'd bring this out. It's one of my favorite pictures. It's called the Maunder butterfly diagram. Here's 11 years in time, and someone has gone through and painstakingly figured out, just looked at the sun and figured out latitude, and then each day where are the sunspots. And you notice it makes this very organized structure. It's called the Maunder butterfly diagram because every 11 years it looks like a butterfly flaps its wings. Now, what is interesting to me about this is that there is a brand new article out in the Royal Astronomical Society's magazine, and it is actually honoring a little bit more one than the other of these two Maunders. This has always been known as the Walter Maunder diagram because Walter Maunder was the scientist who published it. And it was, he published it in 1904, but clearly he and she had to be looking at this data for 4 solar cycles, so at least 44 years or so ahead of its publication time. And what is very interesting is that Annie went through, and I believe it's Cambridge where she got her degree, where she did not get her degree in mathematics, despite the fact that she went through the entire program, but at that time, degrees in mathematics were not awarded to women. So she did everything and came away without a degree. Nonetheless, she persevered in science and she became a computer. This is the name. I can give you the link to this article if you want. It's just published within the last couple of months. And so she became a solar computer. So she went to work at Greenwich, and her job was to, do observing and write things down. I believe that's where she met Walter. She was a civil servant, so as soon as she and Walter married, she had to give up her job, but she was still interested in this. And every day, I guess Walter would bring home the information and they would plot it up. And here we have what is essentially the roots of our understanding of the cycling of the magnetic field. Anyway, she was ultimately made a fellow of the Royal Astronomical Society, and they're celebrating that within the last couple of months. So, and more on that later. Okay, so I have digressed. It's the story behind the event. So let's stand back and think about where we were in the mid-1960s and maybe even how we got there. As a society, the United States has always had this sense of somebody sneaking up on us. It happened in 1941 with the Pearl Harbor attack. Again in 1949 when we realized that the Soviets had gotten plans for the H-bomb and were actively working on it. Thus began the arms race. 1957, the Sputnik launch. I just heard a talk that indicates that was, while quite a shock to the nation, it apparently was not as much of a shock to Eisenhower, who was president at the time. As a matter of fact, there's some indication that he actually knew what was going on and allowed this to move forward and the nation to see it so that we would actually engage in becoming a more technically oriented country. That was one thing that was going on. And the other thing was, once Sputnik launched and it became a situation where Sputnik was actually moving over the United States, which it did in its orbit, then that meant that we were free to launch our satellites and have them move over Russia with the same degree of impunity. And Eisenhower understood that we had advanced technology in terms of our ability to do surveillance that would serve us well. But we simply had to establish, which the Russians did, the right to operate in space. Well, the things kept going on, and pretty soon we were not only operating satellites, but we were thinking about how we could launch missiles at each other, and thus developed the Russian missile crisis, because Russia wanted to have missiles even closer to the United States. Well, let's put them in Cuba, that's close enough. That'll cause a ruckus, and it did. Attack capabilities kept developing, and ultimately by the mid-1960s we had something called mutually assured destruction, which is basically the aggressor could do whatever the aggressor wanted to do, but there was enough residual capability in whoever had been targeted to essentially make the aggressor wish they really hadn't done that. And that was what kept the peace in the 1960s and 70s, such as it was. So this ability to retaliate and inflict as much damage and aggravation as the aggressor had kept everything sort of in balance. In the mid-1960s, however, there were additional Cold War strains. There were the Western and Eastern blocs, which I'm sure you're all familiar with. There were regional conflicts that were acting as sort of proxies to blow out tensions that, you know, didn't want to build up too high between these Western and Eastern blocs. Certainly by 1967, the Vietnam War was escalating. Korean conflict was down to a dull roar. What's very interesting is the date here, 1967, Six-Day Israeli War. On the 22nd and 23rd of May was the day that President Nasser of Egypt, kind of goaded by USSR Syrians, announced that the Straits of Tiran, which is the narrowest part, one of the narrowest straits in the Red Sea, was going to be closed. And of course the Israelis would view that as an act of war, and they did. And so while this activity was taking place on the sun, there were politics in play in terms of global tension, which probably allows you to understand why people would think that we might be under attack, because there were already things going on. So, what was our system to monitor for attacks? It was called the Ballistic Missile Early Warning System. It succeeded something called the Distant Early Warning System, the DEWS line. So I have them all put on here. This is a diagram from, well, I can't even read it. It comes from the U.S. Air Force Museum. But it shows all of the places where we had various types of radars. We had ships or submarines kind of circulating, always watching. And I want to point out these three radars because they were sort of the latest and greatest in technology. They were the Ballistic Missile Early Warning System. They fanned out and looked at about 120 degrees, looking for anything that was going to be coming over the horizon. It would pierce, if it pierced these two fans, then you could actually get a lock on how fast it was traveling, what its trajectory was, and that's what you would be watching for. They were originally built to detect bombers, but as things were developing in the late 1960s, they also realized that, oh yeah, they would intercept, ballistic missiles as well. So, what happened if, something pierced this radar fan? Well, we had alert crews ready to respond, and from the late 50s, early 1960s, they were crews that were sitting in alert shacks at the sides of runways on the aircraft, on the runway aprons, ready to run out to aircraft to get the engines running, and these aircraft certainly carried, did carry nuclear weapons. And so that was essentially that kind of encapsulated our ability to retaliate if need be. One of the issues that was a major concern was something called radio frequency interference. And that is these radars, radio detection and ranging is what a radar stands for, operated at specific wavelengths, and so did the sun. The sun operates at those wavelengths as well. It produces noise. And so you always wanted to be able to filter out that noise. And you had to get it, and so we built filtering systems into these radars. And as a matter of fact, there were a whole bunch of things that needed to be considered and filtered out. And so on the 15th of May, 1967, Department of Defense accepted as full operational capability a very enhanced ballistic missile early warning radar system. Now you think, oh great, nothing can get past it, which I'm sure is what most everybody thought. We have the best ballistic missile early warning radar system in the world, and nothing could go wrong. So if we get a big signal, it means that we've got something coming, or we are being jammed, and that would be the precursor to some kind of system. So the idea is if you jam, these systems, then the other side doesn't know what's coming. And that was a practice, essentially something that was practiced as part of the war games, is to understand that that could happen and how are you going to respond. So, we have that. Now I'll tell you where we were in the solar cycle. So I showed you the 11-year solar cycle. Here we are, here's the Cold War, 1965 is the tick down here, number of sunspots. We were coming up, of course we didn't know what it was going to look like, but we were just at the very beginning of solar cycle, I want to say 20. Solar cycle 20 here. Usually at this time of the solar cycle, there's not much going on, a few spots appearing, no big deal. How the sun managed to produce the radio burst that it did, it remains a bit of a mystery. I've seen some recent work, and we're still trying to figure out how the sun does this, but it did it. So here comes the information on the storms. The source of this great storm in May 1967 was the east limb, meaning it was coming out from this side of the sun over here, passage of one of the greatest activity complexes of solar cycle 20. It was composed of 3 overlapping spots that were converging. They were rotating about each other. They were colliding with each other, which is always a bad sign for sunspots. It means they're way too close to each other. They're really concentrating their magnetic energy. More collisions taking place. So here we have on the 23rd of May that the observers, and these were observers who were just up the road from Lee and his crowd. This was written by the folks in Boulder who are now part of the Space Weather Prediction Center. So we have our own Space Weather Prediction Center as a national resource still operating in Boulder. And we certainly have DoD systems as well. But at any rate, we knew, the civilians knew, that there was a great complex of activity coming in. And I have taken a map pulled from Patrick McIntosh, who charted these areas for probably 40 years. And just this region right in here, so this is the sun kind of laid out in a big map. And this region right in here is highlighted here. And then the sunspots within that region are highlighted right there. So I just keep blowing it up and blowing it up. And where we have these orange dots kind of crossing over these borders and moving across and being across in different color zones is an indication that you have sunspots that are just completely out of order. They are very, very mixed up. They probably harbor a lot of energy. And in fact, that was the case. Out of that region of sunspots, in short order, from 1817 UT, so just before noon, Central United States, came the first great flare. So this dark region right here, so this is shown in negative, it's essentially this region shown in H-alpha light. But there was a great huge flare that snaked across this region, not only once, not only twice, but a third time. And it put out what we call hard X-rays, the most almost gamma ray bursts. It put out soft X-rays, which is how we currently monitor and rate flares. And it put out 1, 2, 3. M is moderate, X is for extreme. So these were very large flares. There was extreme ultraviolet light. It was even visible for a very short time in white light. When a flare becomes visible in white light, it means incredible particle energy being crashed into the sun's surface. It created actually 2 ribbons of light, and in the radio portion of the spectrum, it created these great bursts. And I'll show you what happened with those great bursts. Someone at the time went to great effort to actually draw the sunspots, and you might remember from just playing around with magnets that magnets have north poles and south poles. And in some of these cases, and they should never be mixed together, but the sun managed to mix north and south poles in the same region. And this was one of those regions where the strength of the magnetic field and how fast it was changing from one direction to the other was some of the largest that we have seen then and since. When that flare let loose, when it decided that it had to release some of that energy, what happened immediately in Boulder, and let's see if I can, the HF signal was lost, and I think this signal was one that was being monitored from Illinois. So we're looking at sort of a 13 megahertz signal. These are ones that were just used routinely. They were being generated at various locations in the United States and monitored. This monitoring was going on at Boulder. And here all of a sudden, this is the normal background, and we see these great deviations, and then finally there is so much signal, the ionosphere, the Earth's upper part of the atmosphere that's ionized, that helps us bounce these radio signals, the signal is obliterated. So we had lost high frequency radio signals. Now why would I mention that? It is because we controlled our nuclear arsenal and the aircraft that move these nuclear weapons around by radio signals. If we couldn't contact them, then this was a very bad situation. So suddenly we have not only all of this excess radio energy coming into our radars at high latitudes and confusing the system, but we are in a very significant situation where command and control is threatened. So what to do? And to give you a sense of that right now, that happens on a somewhat irregular basis. So I'll bring you fast forward to May 2013, same level of flare, and here's what the flare level looks like. All of a sudden the flare level goes up. Here's what all of the, not all, but a set of radio signals coming from various places, bouncing back and forth. And these are just ham radio people talking to each other. Here it is before the flare. Here it is still going on just as the flare starts to ramp up. And now we're at the peak of the flare right here. And notice that almost all of this ability to propagate radio signal has been destroyed. So the ability to communicate with anything that needed radio communication is greatly compromised, and then it slowly returns. We get this kind of technology impact on a semi-regular basis with these kinds of flares. A little tiny diagram that basically shows at every level of radio measurement made at Sagamore Hill, outside of Boston on this date, we were over the top. The numbers that would typically come in here is about 100 solar flux units. This is 373,000 solar flux units. Just an unheard of amount of radio flux coming in and just completely blacking out the ability of radio to sort out any kind of radio signal in the northern polar regions. So this is again a more recent event that happened in 2015, but it gives you a sense of where you may not be able to communicate at all and where various other places are being impacted. So what did we end up with? Our radars operating at 440 megahertz were seeing that signal at 370,000 solar flux units come in and just complete, and you think, okay, well, wouldn't they have known that that kind of thing could happen? Yeah, they did. What we did not realize was we actually had things filtered for the over the horizon portion of these radars, but this got into the back lobe of the radars, which had not, no one had thought that anything like that could happen. And there is where we essentially lost or were completely jammed. So even though they'd been recently upgraded and fully tested, they were jammed. We were suspecting that it was actually enemy jamming. Alert crews were responding to this potential act of war. They were headed to their planes, and then the question becomes, well, what is this? Is this enemy or is it natural? Well, that's where Lee comes in. That's where Lee and his crew came in. So where was Lee getting his information? He was getting his information from the optical view, from Sac Peak Observatory. He was getting radio observations from Sagamore Hill. And as I understand it, there was a non-commissioned officer at Sagamore Hill that got quite a nice award for his ability to manage 5 different radio systems and keep them all going during this time. It was an extraordinary result, and that they were able to feed this in to Cheyenne Mountain Complex. So this is down in Colorado Springs where Lee was stationed, where I have been stationed. And then, very interestingly, it had been a slow weather day, so there was a terrestrial weather desk and a solar forecasting desk, and the terrestrial guys always got to go do the weather briefings, but the terrestrial guy came to Lee and his crew and said, anything going on, because it's a slow weather day, and Lee's crowd said, yeah, there's something big going on in the sun. Look, that was 7 in the morning. The event itself took place closer to noon. And so, literally, when all hell broke loose, I think Lee must have said something to, oh yeah, something like half of the sun blew away. Well, it's kind of a smaller fraction than that, but it was a pretty big burst. And so, you know, someone from that early morning briefing remembered that it could be the sun. And so questions went back and forth and up to the Pentagon, down to the Pentagon. You've got crews, you know, likely moving into position at ends of runways, engines hot, what are we doing? And, you know, the thing that was of real concern was, engines hot, what are we doing? And if we do something, will we be able to be in contact with those crews and bring them back? If this was, you know, just the sun up to mischief. Fortunately, we believe, and you know, I was not in SAC, I was not there, Lee was not out on the runway either. So we have only heard through our military colleagues that it ended at just sitting at the ends of the runways, but crews knew that this was not an exercise. So that is where we stood in May of 1967. There have been other foibles with NORAD, many of which have been written up in various magazines, you know, other human errors and this kind of thing. But this is a situation where we had a very natural event beyond any scale that we could have imagined. And the way that we kept things from blowing out was to have the right level of educated people who were astute and monitoring what was going on and able to communicate up and down through the channels and communicate clearly. There is a distinct possibility that this is just the sun being quite mischievous. You can kind of imagine what might have happened if Lee and his crew and others like him had not been present in 1967. So I'm actually there are. Let me see. There's maybe this is what Lee and his crowd were able to do with just very rudimentary data. They were able to project that the BMU system would be recovering in tens of minutes, which it did. The dayside communications challenge would continue for hours, which it did. That the polar cap communications outage would then develop, so the sun had more in store, and that there would be a major magnetic storm with aurora visible. In this case, he did not know it, but it happened all the way down to Arizona. And so, and it was certainly visible in Maine. It was overhead in Washington, D.C., the aurora, about 2 nights later. So this whole system generated an incredible amount of follow-on activity, which the crew at NORAD was able to forecast, and it came to fruition. I can tell you that as a result of this event, the Department of Defense's Solar Forecasting Unit was suddenly viewed as quite valuable. and ongoing funding, and so it is the root of what we now call space weather forecasting in the modern era. It is what got me a Air Force sponsorship to UCLA, where I met George and Nancy, and where they taught me what I know and am able to convey to you. So it was because of very amazing work done with very limited data that we are where we are now. And as just kind of an exclamation point, I will tell you that on the 13th of October, President Obama, that's last week, issued an executive order telling federal agencies who have been squabbling mightily about who gets the resources and who should be forecasting and who does what when, that they should stop that and instead work together, and outlined a very specific set of objectives with timelines saying Department of Defense, within 60 days you will. Department of the Interior, which runs the magnetometer stations that measures the magnetic perturbations on Earth, within 120 days you will do this. And it is something that actually came as a result of work done in the early 1990s by no other than our videographer here and some of his colleagues, to actually start making the civil authorities in the Washington, D.C. area, and those people who work with National Science Foundation, NASA, aware that there was something called space weather, because it had been pretty much in the realm of DOD until mid-1980s, and then there was a massive storm that got into a different part of our technology system, which it actually got into power grids. And the Hydro-Quebec power grid, which is a whole different story, it did in fact come from a similar source, but it was a magnetic storm that came to Earth rather than a radio burst. But after that, people who understood how these things could evolve actually got together with our civil authorities and said, we really need to be paying attention to this. We need, again, to have organized educational opportunities. We need federal agencies talking to each other, and now, as of last week, President Obama has so ordered that. That had actually been going on in Congress, but Congress has been a little stuck of late. And even though something would get, introduced, then there was more fighting. That, by the way, did have bipartisan support. It was not Republicans versus Democrats. Everybody was on board, but there were just other things that would get in the way of getting a bill like this through. So President Obama said this is important enough, and it really needs our attention, and therefore he directed the federal agencies to start moving forward. So I think with that, I will not take you through a whole other slew of slides, and I will just simply say that that we should give a hand to Lee and his crowd, and I will stop.
You want to take questions?
I will. Oh, look at these hands up. Yes.
Was there any information on how the Soviets reacted?
I have received one bit of information from a colleague who is a Russian expatriate now working for the National Solar Observatory, and he told me that he had a discussion, it must have been 1979, I think it was, with one of the very senior Soviet solar scientists, who commented in a rather offhand way that this event funded Russian observatories for nearly 2 decades. But first,
I don't know the astronomical term, but should we assume that the flare was pointed towards planet Earth at the time, or someplace near the line?
yeah, where it originated, if you think of the sun here with its hemisphere facing out to you, it was about 30 degrees off of what we would call central meridian. So a flare, and that actually flares any place on the visible disk of the sun, will put their photons, send them out. But, so it was well positioned.
Yeah, it's interesting to me that the strongest effect of the flare is in the polar region, which also happened to be one of the strategically most sensitive parts of the planet.
Yep.
But so the effect of a big flare would always happen in the polar region?
No, this was rather, this was unusual, and there's a little bit of a distinction that I need to make. Flare is a very general word that describes disturbances across the broad spectrum of energy, all the way from X-ray to radio. And certainly that happened, but in this particular case there was an extreme emission in the radio portion, and that was where we had technology in the polar cap that was just lined up. We'd never seen that kind of burst in the time that we'd been developing that system. Apparently, the sun does this just on occasions. There's good reason to believe, not November I guess it was last November, that a fairly moderate flare may have done something similar to the Swedish air control system. And they're going back and forth, was it the sun, or once again, was it the Russians?
This may be something that's not in your field of purview, but from what you're telling me, it seems as though if the Russians had the capability that we had in 1967 to come to the conclusion that these were caused by the solar storms, would that not be an ideal time to actually start a Pearl Harbor type of attack?
Active point of discussion these days. So, yeah, so you think it's natural. Well, hey, there's a great opportunity. This is, things that play out in orbiters. Yep. Good point. It's being discussed.
Would you care to speculate on how this event compared to the Carrington event of the mid-1800s?
Yeah, so the Carrington event of the mid-1800s is sort of the gold standard of huge events. And it was an event that was pretty much on Central Meridian. It was a flare that Carrington, who was observing at the Kew Observatory, I believe, the magnetometer was at Kew Observatory, he was at Greenwich, and he saw an incredible white light flare. So that meant he saw a flare from the ground. It was something that was so big and across so much of the spectrum that it was actually visible from the ground. You didn't have to be in space to see that one. And the magnetic storm that came from that arrived, I believe it was 22 hours later, very, very fast. The aurora from that storm were seen in Bogota, Colombia, Cuba, and every place in between. In New Orleans, you could actually read the newspaper by auroral light, which was pretty spectacular. So, in terms of magnetic storms and aurora, this was nowhere near. And we did not have radio technology in the Carrington storm. We could imagine that would have wiped out radio technology, kind of as we know it, but we didn't have it then.
I understand that the telegraph operators actually disconnected their batteries and were able to operate just from the aurora's energy.
So as if we could compare that with the March 1989 storm that took out the Hydro-Quebec power grid and put parts of Canada in darkness for many hours, we could imagine that Carrington storm would have been much worse. So in terms of impacts on the things that we consider to be normal concerns, the power grid, that sort of thing, this storm apparently just didn't have much of an impact. But in terms of the radio impact, it was the biggest that we had seen to that point. We've seen one larger than that and you have to ask what part of the radio spectrum, but there was certainly a big event in 2006, and then you have to start thinking about, well, what's the new radio technologies that we have to be concerned about? And whether you realize it or not, GPS operates on radio technology, it operates on radio frequencies, and that was a storm that was big enough to actually be seen in the GPS network, the one from 2006. Would this one have been seen in 2006? It's up for debate. It was kind of on the edge of likely being something that would have been noticed, but probably not disabling for GPS. So you know, to do one-to-one comparisons, well, one solar event always has something that's just off on the side. But the Carrington storm probably had something for everybody that would have been, you know, disabling had we had those types of technologies. One more question.
To what extent is our current electrical grid susceptible to these phenomena, and should we worry about it?
As I understand it, there's actually been a lot of work done in the last 5 to 8 years to understand where the problems may develop. And what happens is when the magnetic storms come in, so it's not the flares and it's not the radio bursts, it's that mass ejection, this thing right here that causes these currents to flow in regions called the auroral electrojets, which could become subauroral. That is where the concern is the greatest. And there's a lot of work going on in terms of hardening the grid. What happens is these currents can actually cause currents to flow in the ground that get concentrated in the transformers that up the voltage from where the generation is going on. You raise the voltage up so that you can transmit the power, and then at the other end you down the voltage, you drop the voltage down so that you can redistribute it. Those places where you're changing the voltage up and down are particularly susceptible to getting extra low frequency currents in, and they will amplify those low frequency currents, start heating, and you'll actually hear these giant transformers making sounds, groaning and grumbling and rumbling. And so we're, you know, kind of working on what are the ways that you can filter that kind of thing out.
One of the things that has been a lot of active work in the last couple of decades since those general outages is they look much more carefully at how to disconnect parts of the grid so that if one part does go down, it doesn't necessarily take it all down.
Not the domino effect that
That's
was
right.
there.
And it's much better today than it was long.
And that is certainly true for the U.S. and Europe. There are developing power grids, though. In 2003, we know that the South African power grid was not as protected as it might have been, and they actually, it was a very slow, over a week or a month degradation of some of their transformers, but it was pretty expensive for them to recover that system. So, you had a question?
Yeah, I toured the solar observatory in New Mexico a year and a half ago, and I understand that that's closing, or maybe it has closed. What do you know about that?
So, it may have, there actually are solar observatories that are being closed so that they can afford the funding to bring up new solar observatories. And so I do believe that there are one or two in New Mexico, maybe one in Arizona, that are being closed, much to the angst of the folks who work there. But I have also recently served on a review committee for the National Science Foundation related to this kind of research. And one of the things that we said is that we do have to be prepared to give up some of our older observatories and their functions so that we can bring up new observatories with, you know, much greater capacity. And that's not always the happiest answer to some folks, but I know that I don't know that this particular observatory is in that situation, but it is the case that in order to bring up some of our new modern observatories that can actually peer and actually see the structure of these magnetic fields on the sun, you're probably going to have to give up something. You can't keep, you know, horse and carriage if you're going to move into a world where you need to be operating superhighways.
I want to say before we close that one of the reasons that Delores can answer these questions with such authority is that she's written a very thick book called Space Weather and the Physics Behind It. And so she is the expert on space weather and the physics behind it. And thank you very much, Delores, for this.